This is the third lecture on electrostatics, electrostatics in dielectrics. Today's topic is Gauss's theorem in electrostatics. Let me first recapitulate what we did in the earlier class. In earlier class, we found out the field at an external point due to a polarized dielectric, and we come upon the conclusion that the polarized dielectric can be replaced by some surface density of polarized charges given by the polarization vector, where n prime is the outward drawn normal and rho p the volume density of charges is given by Now, this was our conclusion that the entire effect of polarized dielectric can be taken care of by these two densities of charges. First, let me come to these two equations. These are field equations or the point equation. Means the left hand side refers to some point and the right hand side refers to the same point. That means if we want to find out the polarization charge density at a point R, then the left hand side refers to the point R and right hand side also refers to the point R. So keeping the primes, one may not keep the primes and write the equation like this. The primes are necessary only when these quantities are involved in integration and there are two variables. One is the field coordinate, another is the source coordinate. So to distinguish between the field and source coordinate, one need to use primes. Now come to the Gauss's theorem. In vacuum, we have learned the Gauss's theorem is this. If you have a Gaussian surface S bounding a volume B, then this is the integral form of Gauss's theorem, which states that the flux of E over a closed surface is equal to charge enclosed by the epsilon, that of the free space permittivity. In differential form, it is the law. Let me see how the law gets modified in presence of dielectric. We consider a dielectric medium which is bounded by a volume tau shown in the rectangular shape solid line, red line, and the closed surface bounding this volume tau is sigma. Within this dielectric, we consider an imaginary surface or fictitious surface S denoted by the dotted line which encloses the volume B, and within S there are few conductors S1, S2, S3, and on each conductor there are charges. On S1 Q1, on S2 Q2, S3 on S3 it is Q3, and so on and so forth. First thing that we want to find out, what is the charge enclosed by the surface S. Now we know that the polarization charge occurs in entire volume, which is taken care of rho p, and on the surface separating two media, and this is sigma p. Now, if we consider what is the total bound charge? So, total bound charge QB, in this case, it is the Q1 charges on conductor, and this is the total bound charge. Now, coming to the this is the total free charge. This is the total free charge on the conductor, and coming to the bound or polarization charge QB, they are the charges on this surface. So these are the, so on surface 1, the charge on surface 1 is a closed surface S1. This is sigma 1 P ds, and such surface there are 1, 2, and there are so many surfaces. So we write it as summation over I, where sum runs over all the conductors within S, plus the volume distribution of charges. Now you write this, the expression for sigma p. And for this, we can convert this volume integral into the surface integral using Gauss's theorem. But one must be careful in converting this volume integral into surface integral. In doing this, there are surfaces that bounds the volume is S1, S2, S3 up and also S. So this can be written as minus this contribution first the S this two contribution gets cancelled, leaving this one only. This is the total bound charge. So if you want to replace this Q enclosed, so this Q enclosed, so I just write the summary. This becomes equal to minus C. So the total charge within the surface S is Q enclosed by the surface is QF plus QB. So QF when and if we write this one in Gauss's theorem and this epsilon 0 is multiplied to this, we get or this quantity warrants a new name and we call it D, and it is historically called displacement vector, electric displacement vector, and is equal to QF. So the displacement vector, the total flux or the total flux of D vector is simply Q, the free charges enclosed in the surface. So if we compare this law in the in the presence of dielectric, this becomes and if we write that the free charge density as rho f dv over v, and if we convert this into volume integral, we readily get divergence D is equal to rho f as the differential from Gauss's law in dielectric medium. So these two statements of Gauss's law in free space is replaced by these two. Instead of going into this calculation, we can simply come to the this calculation. Before going that, let me say something. This divergence, the divergence of D is related to free charge density only. There is no polarization charge, but the effect of polarization is taken within D because D is this vector. If you place a charge particle Q, particle of charge Q in an electric field E, it experiences a force Q times E, and we can measure experimentally the force acting on a particle. So it is the electric vector which is susceptible to the direct measurement of experimental measurement. In that sense, E is the fundamental vector, but D is simply an auxiliary vector, because if we know the free charge density, then we can calculate from this the divergence of D. So we can get an information about the divergence of D from the free charge density. In that case, D introduction of D vector facilitates our calculation. We could also start the Gauss's theorem from its differential form and can come to the same conclusion. Let me do that. We know that the in the differential form, the Gauss's theorem is epsilon times divergence E is equal to rho. I have multiplied this with this, and for rho within the presence of dielectric medium is rho F plus rho P, the free charges and the polarization charges, and the polarization for polarization charge is given by, so if we take this out on the other side, we get divergence of the same equation that we obtained earlier. There is yet another phenomenological way of arriving at the Gauss's theorem. This calculation involves a bit complicated mathematics, but the result is elegant. Let me also go for this. So this is another third way of deriving Gauss's theorem of electrostatics. What we do, we consider a polarized material bounded within a volume V prime and a surface S prime. Within this material, we consider a volume element around our source coordinate R prime, and we want to calculate the field at this point, and this is R is the relative vector that we always use the same convention. So what is the potential at the field point? The potential at this field point, if we write, this is phi E at R. This first let me write the SI factor. Then there are some free charges within this volume, so there will be a contribution to the potential coming from the free charges. And there are some polarization effect. Since the polarized material is electrically neutral, it doesn't have any monopole moment, and in dipole approximation we consider that it is sufficient to consider the induced dipole in order to describe the effect of a polarized material. So under dipole approximation, the polarized part is here we have used the P dV prime is the dipole moment within this of the material within this volume, and it produces a magnetic and electric potential at the point R is P R prime dV prime dot R by R cube. This is the term that we have used. Now we can use Nabla operator. First let me to do one thing. To save lever, I just write this 4 pi epsilon naught part on this side. So this way, and this becomes nabla is nabla operator with respect to the source coordinate, and this is equal to vector r by r cube with a positive sign. So this is the potential. We want to find out the divergence, the source term of the electric field. That is, we want to find out divergence of E. Divergence of E, and we know that it is divergence of minus grad of phi E at R. In that sense, it is minus so divergence of E, and if we is again this 4 pi times factor when multiplied on this 4 pi epsilon 0 times divergence of E at R. I want again we specifically write the argument is the nabla operating on this, and I'll also take the minus sign this side. So it is simply note that this differentiation is with respect to field coordinate and integration with respect to source coordinate, and they are independent of each other, so we can exchange the order of integration and differentiation. And furthermore, this does not operate on this because it is a function of the field source coordinate. So the Laplacian operates only on 1 upon R, and similarly Laplacian also operates on this. So we write it as here we also exchange the order of differentiations. Now, what is this? We know that square, it is also is equal to minus 4 pi delta of r minus r prime, because r vector is r minus r prime, or this is equal to minus 4 pi delta of capital R. So if we write this minus 4 pi factor and cancels this, and we get the epsilon 0 divergence of E on the left hand side. This is equal to integration over V prime other factors has already been adjusted. This is for this, and for minus 4 pi factor has been adjusted. this part on integration readily gives you rho f at r, the free charge density at r, but the second term is a bit complicated. If we recall the properties of delta function, that is integration f of x x prime delta prime of x minus x prime dx prime is minus a prime of x. If we use this property, then this comes out to be this part becomes a minus sign minus this prime. So here the derivative, and this is derivative of p. The derivative comes in the form of divergence, and this is equal to divergence p at r. This is one way of getting the result. If we do, and I will also illustrate this evaluation in another way which would be convenient for you. So let me first write this. So this becomes rho f at r, and this part is minus divergence of p at r, which again leads to the Gauss's theorem. Gauss's theorem in dielectric in its differential form. So again we land up with divergence of d is equal to rho f, and it is a point relation, means left hand side and right hand side refers to the same field coordinate. The thing that is left, the evaluation of this part in an explicit way, so that we could satisfy ourselves that this is the result indeed. Here, in coming to this result, I have just used the property of delta function and calculated this term in a single line. Let me come to evaluation of this term in an explicit way. So the problem that is left is to show that the integration over v prime p r prime dot this is to show. We take the x component of this, or if we write this part explicitly, this becomes px at x prime y prime z prime. This x prime y prime z prime for r prime dot for this del x prime, and this operates on delta of x minus x prime, delta of y minus y prime, delta of z minus z prime. Recall the property of delta function, and for dv it is dx prime, dy prime, dz prime, and integration over v prime. Now we first have the del x operates only on this term. These two are free. So if we calculate y prime integration, this will be y, not prime. If we calculate z prime integration, it will be z. So result is px, note the x prime, yz, not y prime z prime. And this is del x prime, delta of x minus x prime dx prime. If we integrate it in parts, first part is the first function unchanged, integral of the second. Integral of the second is a delta function which gives you 0 minus derivative of the first and the integral of the second. So this second part is minus. Derivative means del x prime of px prime at x prime y z, and this is delta x minus x prime integrated over x prime. This is simply del x of px at x y z. If you consider the y component, it will be y py z pz. So if we add these three components, it is the result. So by this we end our discussion on Gauss's law of electrostatics in dielectric medium.